Okay, hi. We're now looking at 5C in the textbook and we're looking at the applications of differentiation. We're still looking at exponentials and we'll come to logarithms soon. So we're now extending our problems on differentiation to include the exponential function. We've had a little look at that in year 11, but we're just going to look at it a little bit more. We looked at questions a little bit in year 11 about exponential growth and exponential decay, and the HSC likes to question us on these areas, so it's something that we need to be pretty confident with, I think. Familiarity with the graph will assist in understanding the behaviour of any function that includes an exponential component. So whenever we see an exponential in a question, we really want to think about what that exponential is doing to the graph and the data that we're looking at. So here you'll see over to the right, we've got the red graph, which is y equals e to the x, and we've got the green one, which is y equals e to the minus x. Those two are mirror images, so they're reflected through the y-axis, and that's what that negative sign does. Both e to the x and e to the minus x cross at 0, 1, and the slope at 0, 1 is 1. So if we were to differentiate e to the x, we'd get e to the x, and so the gradient at the value of 1 would be equal to 1. So if we put e to the 0 would be 1, so that would give us our gradient at this point. Likewise, if we were to differentiate e to the minus x, we'd get minus e to the minus x, and at x equals 0, we would find that our value would be 1. So we'd get a gradient of a tangent, and I don't want to mess the diagram up, but if we had a tangent at e to the x at 1, it would have a gradient of 1. If we had a tangent at e to the minus x at 1, it would be, we'll call that m2, minus 1. And what we'd find that these two tangents of e to the x and e to the minus x at 0, 1 would actually be perpendicular. So that's a handy little tip to know, and that's that third point down there. What we say is, and you might have heard of these words during COVID. We talked a lot about, or the news talked a lot about the graph of how the COVID virus was growing, and it was growing exponentially. And that's basically what this graph is doing. It's an exponential graph, but it's growing exponentially. So the e to the x, as we move towards x becoming infinity, the graph is getting extremely large. And that is where the word exponential is coming from, I guess. E to the x is growing exponentially as x gets really big and goes to infinity. Likewise, the opposite, and I might just highlight those. We've got grow. Grow means get bigger, and decay means get smaller. So with e to the minus x, as x goes to infinity, so same direction, but this is the green graph. As x gets really large, our exponential graph decays and it gets really small, and it hits along the x-axis, which is our asymptote. So those words are something that we're going to be looking for in questions, growth and decay. They might talk about that, or we might need to talk about that in terms of what our data is doing. Okay, let's have a look at the next little point down here. It's called talking about a dominating component. So as the value of e to the x varies significantly, so as we're moving from 0 up to infinity, we get a lot of change in our graph. We're either getting really large or we're getting really small. So any function then that is multiplied by e to the x will be greatly influenced by the exponential component. So basically, if we're multiplying anything by e to the x, that's going to take charge, and what we say is it basically dominates, and that's down here a little bit further, but e to the x dominates any other graph. It says when the value of one part of any function contributes a significant portion of the value, we say that it dominates. So for example, the function x times e to the minus x, as it's going to go to 0 as x goes to infinity. The reason that's going to happen is because e to the minus x is our dominating term, and the actual curve e to the minus x is going to 0 as x goes to infinity. So we're assuming that x e to the minus x is going to do the same, because always our e to the x and our e to the minus x are going to be dominating terms. So that's something that you need to be aware of. And we'll have a look at that below when we have a look at the next example. So what we're going to have a go at doing below is sketching the graph of y equals x e to the minus x after completing the following steps. So we're going to write the domain, test whether it's even or odd, find any zeros, examine the behavior as x goes to infinity and minus infinity, find stationary points and find any points of inflection and examine the concavity. So these things are things that we all did in curve sketching already. We just haven't done a lot of it in terms of the exponential. So let's have a look at that below. Okay, so we're going to remember while we're looking at this graph, and I'll just highlight it there for us, that our e to the minus x is going to dominate our graph. It's going to take charge, basically. So when we're writing down the domain is our x values. What x values can this graph take? So let's have a look at what's happening with e to the minus x. Let's have a look at it up here. E to the minus x is our green one. E to the minus x can take any values of x. So our x e to the minus x is going to be able to take any values of x. So we're just multiplying x e to the minus x by values of x. So we'll say all real x values for that one. Okay, so part B wants us to test whether the function is even or odd and find any zeros of the function, including their sign. So testing whether they're even or odd, an even test, we're going to test that f of minus x is equal to f of x. For odd, it's f of minus x is equal to minus f of x. If none of those occur, then it's going to be neither. So we've got that our f of minus x would be equal to minus x e to the x. That does not equal f of x. Does it equal minus f of x? No, it doesn't. So we're going to say that it's neither even nor odd. Okay, so we're finding whether there's any zeros. So zeros happen when our function is crossing the x-axis, and that happens when y is 0. So that would happen when x e to the minus x is going to be equal to 0. That's going to happen when x equals 0. And e to the minus x can't equal 0, so it's only going to happen as x equals 0. So that's going to be our only 0. So we want to have a look at the sign of the function as well. When we're looking at the sign of the function, what we're doing is we're putting in our x and y values and figuring out what the sign is, either side of our function, at the 0 value. So our 0 is x, and we want to find values our 0 is on x, our 0 is 0, and that's our x value. We want to look at values either side of 0. So I'm going to pick 1 and I'm going to pick minus 1. Remember, we always were picking nice, simple values that were close to when our 0 was going to be. So we're popping in these values at minus 1, 0, and 1 into our function up here. We know that our 0 value is going to be 0, so there's no sign there. But for minus 1, we'll pop minus 1 in there. I get minus 1 e to the 1. So I'm going to get a minus e value there. For this one here, I'm going to get 1 in there. It's going to be 1 times e to the minus 1. So I'm going to have e to the minus 1 there. Minus e is going to be a negative value. I might just put a little squiggly line there. And e to the minus 1 is going to be a positive value. And if you're getting what that does, I'll just do a quick sketch, but we'll do a little neater one later. All that's telling me here is I've got a 0 here. I had a testing my value here at 1. I'm testing my value here at minus 1. We know that at minus 1, our sign is negative. So at minus 1, we're going to be down here somewhere. At 1, we're going to be positive. So that's all we know from the signs of the values so far. And we'll come back to that diagram. C. What does C tell us? C is wanting us to examine the function's behavior as x goes to infinity and as x goes to minus infinity, noting any asymptotes. Okay, so next we want to have a look at what happens as x goes to infinity. So we have a look at the graph up here as it is as a function written. As x goes to infinity, so this value here, x goes to infinity, it's going to be times by e to the minus x. Now, e to the minus x, as x goes to infinity, if we have a look up here, it's the green graph, is going towards 0. So that section of the graph is going to be taking the dominant part, so it's getting closer and closer to 0. So what's going to happen is, yep, this part here is going to infinity, but it's being times by a number that's nearly 0. So as x goes to infinity, what we're saying is our function, or our y, is going to 0. So the x-axis is actually going to be an asymptote still for this graph. Now, as x goes to minus infinity, that's a little bit different. As x goes to minus infinity, our y equals e to the x becomes really large, but it's being timesed by a negative value out the front. So it's going to be a large negative value. So as x goes to minus infinity, y is going to be going to minus infinity also. Okay, so D wants us to have a look at any stationary points. So thinking back to what stationary points had happened, stationary points were happening when our first derivative is equal to 0. So we need to differentiate our x equals e to the x, and you're going to need to use a product rule for that one. So if you want to pause the video and have a go, and we shall get our solution and have a look at that together. And so check you got what I've got. I've got my u and my v down there. I found my u dash and v dash, and I just popped into the product rule, which is written on your formula sheet, so you don't need to memorize it. Go and have a look at it and copy it down, and I've ended up with my y dash is equal to this value here, e to the minus x e to the x. Now, our stationary points happen when that first derivative, y dash, is equal to 0. So I want to set this equal to 0. So I'm going to have e to the minus x, e to the minus x is equal to 0. And what I note, though, is I could factorize that. So e to the minus x out the front, 1 minus x in my brackets, and I need to factorize it in order to get that to work. Setting each part to 0, I can have e to the minus x is equal to 0, and 1 minus x is equal to 0. This has got no solution because e to the minus x doesn't equal 0 because there's an asymptote as the x-axis being our asymptote, and here I've got x is equal to 1. So our stationary point happens when x is equal to 1. When x is equal to 1, we need to find y because it wants the stationary point. Y is going to be equal to 1 times e to the minus 1. Okay, now we could examine the concavity of that stationary point by looking at the second derivative, but I already know that at x equals 1 from my part B up here, at x equals 1, I was positive. So I'm going to have a maximum at that point for my stationary point. So I don't need to actually have a look at that any further. I don't need to examine that. But I do now need to have a look at the points of inflection, if there are any, and find the concavity of that as well. So in order to find our inflection points and examine their concavity, I've just jumped back into our calculus sketching using curve sketching using calculus that we did in term 4 last year, and just pulled out this little table. And we should remember that when our second derivative is greater than 0, it's concave upwards. Okay, so it's a positive one, and we have little eyes in there and a positive face. When our second derivative is less than 0, it's negative, it's concave downwards. The third one, when our second derivative is 0 and there's a concavity change either side of that, then it's a point of inflection. So that's what we need to do here for this question, is look at that third one to find any points of inflection. So we want to find where the second derivative is equal to 0, okay, where our y double dash or our second derivative is 0, but we need to, in order to do that, figure out what our y double dash is, okay. So let's do that to start with. So if you want to pause the video and start working on that, we'll get back to looking at it. Hopefully you've had a go, but if you're stuck, what we're wanting to do is we're wanting to go and have a look at what we found as our first derivative. That was our first derivative here, factorized and unfactorized. I would be using the second form here. Otherwise, we're going to have to work out, it's just going to be a little bit messier. So let's do that second form and we'll do a product rule again. So we'll start with our y dash is equal to e to the minus x times 1 minus x equals 0. Let's have u being e to the minus x and v being equal to 1 minus x. Now make sure that you're doing it as a product rule because there are two separate functions multiplied together. They both have x's in them, so there's both independent little functions that need to be treated separately, hence the product rule is needed. So our u dash is going to be equal to minus e to the minus x, and our v dash is going to be equal to minus 1. So the product rule says that we want to have v u dash plus u v dash, or v du dx plus u dv dx. Do not memorize this. Please go and write that down from your formula sheet. So our v du dx is that way, and our u dv dx is that way. So we're going to end up with minus e to the minus x times 1 minus x, which is our v du dx, and our u dv dx is going to be, taking away from that, I'll just get rid of the plus sign in there. Let's go and get my pen to work for us. There we go. Minus e to the minus x. That looks very messy, so let's just see if we can neaten that up by expanding out to start with. So we're going to have minus e to the minus x plus x e to the minus x, and we're going to have a minus e to the minus x again. So we're going to have two lots of minus e's to the minus x in the negative direction, plus an x e to the minus x, and we can also factorize that out by e to the minus x, and we'll end up with minus 2 plus x, but I might write that as x minus 2 just to neaten that a little. Now remember what we're trying to do is we're trying to find a point of inflection, and that would happen possibly when the second derivative is equal to 0. So when this is equal to 0, so we want to find out when e to the minus x, x minus 2 is equal to 0. E to the minus x doesn't equal 0. It always gets close to 0, but doesn't actually get to 0. So that's not going to help us. But x minus 2, we can set that to 0, and we'll end up with x equal to 2 being a possible inflection point. Okay, but you need to test that it is, okay, because part of that is testing whether it is a point of inflection. So we want to have a look at either side of that point and see if there is actually a concavity change. So let's do that now. So here's my stationary point here. I know that the second derivative there is 0, so we're not looking at the concavity there, but we're looking at a concavity either side. So I want to try a number either side, so 3 and 1. If we pop those into our second derivative, which we've got nicely written just here, okay, if I pop 3 in there, I'll end up with 3 minus 2 is 1, and I'll end up with e to the minus 3. Either pop that in your calculator and figure out what we've got. We're actually going to have a positive value for that. Otherwise, you can have a think what the graph's doing at e to the at x equals 3. Here, we're still going to have a positive value. We're looking at e to the minus 3 to be down here somewhere, so it's still positive. Otherwise, your calculator can do that with you. When x is 1, we're going to have e to the minus 1, and it's going to be times by minus 1, so we're going to have a negative concavity. So there's a change in concavity. Therefore, we'll say since a change in concavity, triangle means change, then x equals 2 is an inflection point. Okay, so that's a lot of information that we've worked through there. We need to go back to the question because it actually wants us to sketch the graph of that. So let's get organised and sketch that graph. Okay, so I've got some axes drawn over here. See if you can squeeze those in there. Now we need to go back and look at everything that we did and see if we can figure out what our graph's going to have a look at. So we know our domain is all x values. So we're going to be okay across all of our x values. It wasn't even or it wasn't odd. It was neither. So that's not going to help us at all. But we also figured out that there was a stationary point at x is equal to 0. So there's something happening at x is equal to 0. Now it does get a little bit confusing. We're going to think, what does a stationary point mean? A stationary point is where a graph cuts the x-axis. So it's going to be cutting the x-axis there. We also knew when we tested that stationary point that at either side of that stationary point, we had at -1, we were negative, and at 1, we were positive. So we know that down here at -1, we're down this area somewhere, and at 1, we're up here. So that gives us a little bit of help. We don't know really what's happening there. Let's see what else we learned. We knew that as x went to infinity, y went to 0. So we know down here that it's going to be up here. As x goes to infinity, y is going to be 0, and we're assuming And I think we're accurately assuming that we're going to have the graph on the positive side because we knew we were positive at 1 up here. We also knew that as x went to minus infinity, y went to minus infinity as well. So we know that as x gets big, y gets big, and we're down this side, so we're down here somewhere as well. We know those two things. Let's see if we can figure out what else is happening. I haven't seen the graph yet, so I don't know what it's going to look like. Stationary point. So we knew there's a stationary point at 1 and e to the minus 1. Let's have a look at that. Okay, so a stationary point at 1, e to the minus 1. So here's 1. E to the minus 1 would be a really tiny little number. So again, if you're not sure what that looks like, just pop it into your calculator. So that's here. And we worked out that that was going to be a maximum stationary point there. And we worked out that because of what was happening over here. And we also worked out that there was a inflection point at x equals 2. So we'll pop a 2 down here. We'll fix that up there. At x equals 2, there was an inflection point. What was our y value when x is 2? We didn't have a look at that. Our y value when x is 2 would be 2e to the minus 2. This inflection point here, to the right of our 2, we knew that it was a maximum, and to the left it was a minimum. So it's going to have like a little turn around like that. It's going to go up here. It's going to cut down there, and it's going to go down that way. And it probably needs to be a little bit more curved than that. Let me fix that up. And that's what my graph is going to look like, a little bit neater through there. That gives us a bit of an idea of what it looks like. And yep, that is what it looks like. I just checked that. So we're on par with that. Okay. Have a go at the exercises, guys. If you've got any questions, you're going to come and see me in exercise 5C.